You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Hello, this is Richard Jacobs with the Future Tech Podcast, and I have Dr. James Kell. He's a technologist. Dr. Kell is part of Rolls-Royce, the famous engineering company. So, James, how you doing? Thanks for coming.
Hi.
Yeah. So, tell me about your work. What are you working on? I read a brief description, but in order to give it justice, I'll ask you about it. So, what's your work involved right now?
So the kind of shorthand version of explaining what we do is, or what I'm doing with the company, is developing new technologies for keyhole surgery for jet engines. So really, this is based on the fact
jet
that
engines.
That's right. Yeah. So we make jet engines in the company, and a lot of those things go on planes. They also go into the bowels of a ship, and they also maybe generate power on land or pump oil on land as well. So it's kind of, they get distributed all over the world on air, land, and sea. So we're basically trying to make them serviceable and operate to their expectation when they're out in the fleet. So there's big penalties for us if we have to remove them early and dismantle them. So the intention is
what about having technicians go on site? I guess in certain, they're probably located in claustrophobic environments, or maybe even dangerous or inaccessible environments once they're in service.
Yes, they can be. Yeah, they can be. The kind of people that we send out to do these jobs are always highly specialized as well. They're very skilled engineers themselves, and they're not there's not loads of them around. So we always are looking at different ways to kind of either make their jobs easier or kind of make them more capable and able to be more effective.
So I guess there's various ways you could do this. You could try to do, distance engineering, and that's maybe what's part of the solution is. And then, you need to get to the engine without getting to it. And then once you're there, you don't want to tear the whole thing apart to fix it. So I guess all those reasons for keyhole surgery make sense.
Yeah, sorry, I kind of came in early and sort of given you a sort of strapline keyhole surgery for jet engines, but really the whole basis that it's built on is the fact that all of our products are, generally speaking, under long-term service agreements, which means if we have to remove one of those engines and replace it, then it costs us a lot of money and it disrupts the customer use. So we don't want to do that, and the customer doesn't want us to do that. So yeah, we try to inspect and repair out in the field through these tiny inspection holes that they're about. Basically, if you can kind of fit your finger in, that's a pretty good rule of thumb, so to speak.
Can you give a general ballpark of the amount of money involved if an engine's out of service, per day, or if it has to be, if someone has to go into the field and replace it or work on it?
Yeah, I mean, if you're thinking of a nuclear reactor, then the numbers associated with that are, there's certainly a six-figure sum in terms of outage per day as a penalty, and the same sort of things apply, generally speaking, if you're having to remove a jet engine from the wing of an aircraft. It's also approaching that sort of figure in terms of how much it would cost us to remove it and replace with a spare engine and then fix the old one, etc., etc. So the numbers in terms of cost avoidance are six-figure dollar sums, so it's significant.
Are you working on existing products out there to modify them or allow you to work on them in a keyhole fashion, or are you working with the engineering department on new products so that they're designed where it's easier to do this kind of work regardless?
Yeah, so both. The answer to those questions is yes to both. We are working on we've got legacy engines that have been designed sometimes down in the 60s, and they're still flying around now. Certainly in the smaller military aircraft, we've got that kind of challenge ahead of us because we don't have computer-aided design models, for example, of these old engines. We're just kind of working off paper almost. And they've been designed with some level of service possibility. So there are inspection ports along the side, and obviously you can get in at the front and the rear. There's quite big access holes there where the air would normally pass, but it does make things difficult. So we are looking at working with our future programs group to develop new ways to maybe allow more serviceability with the engine. So kind of a more design for service approach. And some of these things actually also bleed into having things live on the engine for its life, such as a permanently embedded camera network, for example. So we already have a engine health monitoring network that monitors vibration and pressure and temperature, etc. But we've not introduced a new sensor for decades. So we've been working on a project that enables us to permanently embed a camera network, which basically gives you eyes to the ears of the engine health monitoring.
Yeah, that's interesting. How are the products different now from 10, 20, 30, 40 years ago? Are they more complex? Are they easier to work on? What's the evolution?
Well, yeah. Sometimes they're easier. Sometimes they're not. I guess there's a lot of challenges in terms of externals that are becoming more and more kind of in our way. I suppose we're trying to get through an engine casing into the high value parts inside the engine, and we're having more and more pipework and things and kind of wiring, etc., around the engine nowadays. But the other problems are to do with the fact that there's more exotic materials to allow these engines to run at sort of higher temperatures to make them more efficient, etc. Different materials such as kind of composites are making things more difficult nowadays. But then it comes with the fact that we're trying to design it from a repair perspective as well. So you kind of counterbalance some of those things because we may be able to design more inspection holes, for example, whereas you just get what you're given from an engine that's already flying now. That was designed maybe 10 years ago, for example, when we weren't really thinking in this way so much. But generally speaking, they're very, very similar. They're very similar. If you were to look at one of our old RB211 engines from the 80s, they're very similar in its kind of core capability to what you see flying around tomorrow. There will be a few big changes, but they're a few more years away in terms of our new architectures.
Then now getting to the exciting part. So how do you do keyhole surgery on an engine, or how do you work on them through a keyhole-sized opening?
Yeah, so I said the keyhole size is approximately 10 mil, so you can basically get your finger in, and that basically means we work with a lot of medical equipment, and that's hence the kind of the phrasing keyhole surgery type stuff. But there's things off the shelf that you can buy nowadays, video scopes and other types of non-destructive evaluation technologies. We can always, for some time, we've been able to kind of pass those through inspection ports and get some information and maybe able to inspect an engine to confirm it's safe, for example. But we're trying to take those things a step further. We don't just want to be able to inspect and see and find a problem. We want to be able to find that problem but do something about it. And that could mean removing some material, or it could mean adding some material back on. And both of those two processes, in the broadest terms, can be considered repairs. And we can get into kind of all sorts of different sort of technologies and processes that we're developing because we want to try to effectively miniaturize what we can do in a component repair shop, but on the end of a miniature snake robot, for example. So these kind of snake robots that we're developing with our partner in the University of Nottingham, we're really striving to push the boundaries of what's possible. So the smallest one we've made so far is 6 millimeters in diameter, but it's quite short. It's only about 200 mil long at this stage. But we've made ones that are 1.5 meters. We've got one on the design board at the moment that's going to be 5 meters, and they range in terms of that, like I said, 6 mil up to maybe 20 mil or so. And we're able to, with pulling parallel cables and making very small segments and little discs effectively that get stacked up together, we're able to drive these things with an awful lot of skill and sorry, I should mention a lot of the design effort that is done by the University of Nottingham, both in terms of hardware but also software, is actually the computer control aspects that make these things real. Because we're trying to maybe in some cases control a 24-degree of freedom robot, which is not an insignificant challenge.
Well, there's getting the robot in there, worming its way in. But then once you're in there, how do you? I mean, what kind of repairs are needed? Do you have to cut? Do you have to transport? Do you have to bring in new material? I mean, it seems super hard to be able to do much even when you're in there.
Yeah, it is hard, and it's one of those things that sometimes you wonder when you wake up in the morning whether you're just banging your head against a brick wall, because there are some significant challenges. But when we get something right and we're able to kind of effect a repair, it's very kind of rewarding in both in terms of satisfaction, but also from a monetary perspective, kind of cost avoidance. We talked about the savings earlier. The kind of repairs that are needed are, generally speaking, if we find some kind of an edge feature, like a dent, for example, we wouldn't want to leave that on a blade if we saw that. So we would traditionally remove some material by grinding, for example. So this would remove a dent, and it would make a kind of stress-relieved scallop shape that is safe to fly on until the next time the engine would come in the overhaul shop, where we would just swap that blade. So when I mean coming into the overhaul shop, I mean it would be stripped down, and then we would replace the part that we fixed out in service. And it sounds a bit crazy to say a repair is removing some damaged material, but really that kind of makes things safer, because we don't want a crack to form and then to grow and then to release the blade, because those things are dangerous.
I just imagine like a snake with a big piece of chewing gum, forming its way into the engine and sticking it in place.
Yeah.
But I know you wouldn't
quite.
do that.
That's it. No, not quite. But I mean, the kind of concept is the same. Yeah, absolutely. So it's kind of, we're developing with companies miniaturized laser control systems so that we can feed in via a fiber a laser to remove material in very specific areas. We've done it with grinding tools. So, I mean, basically kind of getting a dental drill, actually, and putting it on the end of a snake robot. That's the kind of thing we've been doing for the last couple of years. And we've got a good level of control where we can, just with a fairly rudimentary grinder, but in the end of a dental drill, can remove some material in a controlled way, or we can make it remove material in a controlled way, I should say. It doesn't sound very good, because you've got a big snake robot inside the engine, and it sounds like you're at the dentist. So it's a bit, people don't like it, but it's actually doing quite a good job, if you see what I mean.
Well, I could see this to be a back and forth. As you design the robots, they get in there and they work on stuff, and they get stuck, or they're able to do certain things and not other things. That informs the design of the engine, so it wears in a way that the robot can work on it, for instance, or it. I see this interplay back and forth between the two efforts.
Yeah, there are definitely the guys in the new design area for the new engines and things, the new products that we're making. They are we're pretty closely aligned to those guys. They're up to speed in terms of what we are developing, and they're trying to basically give us more access ports. But the reality is, those things designers don't want on the side of the engine, because they're a leak point, and we've worked really hard to compress the airflow going through the engine. You don't want to arbitrarily put a hole in the side where we can come along when we need to, if we need to kind of do a repair. The engine still has to go through its life, compressing air and then pushing it into the combustion chamber, etc., and ultimately providing thrust to the people flying the engine. But there's definitely an interplay, and basically what we could say with the engines we have around us now is that they've been designed as they were, without this kind of capability in their minds. So we are effectively trying to do whatever we can, I suppose, with what we have in front of us.
Are you able to go in through the intake or the exhaust of the engine, or is it too small to be able to do something like that?
No, we can do that. It's just, it very quickly becomes a bit of a forest of blades, because you can appreciate, if you look at the front of a jet engine, all you really see is the fan. But what's behind the fan, right down at the hub of the fan disc, if you like, is a series of of stator blades and another row of moving blades and then another row of static blades, etc., etc., etc. And that there may be 8 rotating stages in the first part, and then there's another 6 in the bit after that. So it quickly becomes a very, very tight forest of blades to kind of slalom through. So it's quite difficult to do that. So we do traditionally like to go through an inspection port to the side. But yeah, those things are open to us and available. If the area of the repair site, if you like, is nearer the front or the back, then yeah, absolutely, that's definitely a way in.
Well, I figure there's a Pareto of the problems that happen most often. Do those happen to coincide with what the robots are good at? And I'm sure that's what's in front of you, like stuff that's rare. Who cares? But the common stuff.
Yeah, quite.
I don't even know if you could say what it is, but can you say like
no,
one
you're right. Yeah, and well, there's not often one common problem, and if there is, then there's lots and lots of people working on it to make sure it doesn't become an issue. But yeah, we often look at the Paretos, and we're working always with the service guys just to make sure that we understand what the big drivers are for removing engines early from service, and seeing if we can make sure that our technology is addressing those needs. It's very often the case that the thing that drives an engine off early is something we can't do anything about, and that's something we just have to take on the chin. And obviously we want to work on those kind of bigger problems, but sometimes those things are just too much of an issue to work on. And sometimes, actually, because of the nature of these developments, the problem might have shown up early. We've got concerned about it enough to develop a system or a solution, and by the time it's ready, we might have ended up kind of missing the boat, if you like, because those engines might have come in for their service and been repaired in the component shop. But what we're aiming to do, and we're getting very close to this now, is have a sort of a portfolio, if you like, of those types of projects that have been designed and sort of put on the shelf, that we can take elements of this project and take elements of this thing and kind of put them together in a sort of Frankenstein's monster type way to kind of end up with a thing that we would never have conceived, but would be able to quite quickly be modified to address a problem that is in front of us tomorrow. Does that make sense?
Yeah, as you were talking, I was thinking that there's probably 2 things that come up. Like I'm sure the company has worked very hard to get rid of, problems that occur frequently, so you're left with problems that occur infrequently and weird ones. And then I thought, wait a minute, what about the maintenance? Lots of weird ones. Yeah.
Well,
I thought the first win would be like, being able to lengthen the maintenance schedule and do some of the maintenance in situ. So I was going to ask you about that.
Well, that's really the root of that project, that we're putting these miniature embedded cameras in to the engines. We're interested in doing that to kind of help us understand the engine life cycle more often and be able to be maybe more customized with our approach to service offerings. So if you're understanding more about a particular airline flying in the Far East compared to a particular airline flying in Africa, for example, or in the Middle East, those things, maybe they might be the same product as far as we're concerned, but the operators would be using them in a different way and operating them in a different place. So we're able to get visual information quickly by having these embedded cameras. That means we can automate the inspection, we can make decisions quicker, we can maybe say, we can kind of get towards predicting the maintenance schedules, understanding issues as they arise quicker, and suggest things, such as, you might want to thrust down on certain flight cycle areas or whatever it is to kind of maximize the efficiency of the engine, for example. These are the kind of things we're trying to kind of get into the next sort of phase of being more, I suppose, digitally orientated in terms of our service offering. I know it's a bit of an internal buzz phrase, I suppose, but it is really what we're trying to do, be quite customized with that.
Yeah, I could see if a certain maintenance type can happen, or should happen every 1 to 3 months. If you had cameras on all the engines, you could see, this one can go the full 3 months, but this one we got to get early. So it would make things a lot more efficient.
Exactly. That's right. And we do thousands of inspections every year. And, and I'm not going to pretend that this embedded camera system would help you do those things and eliminate them all, because it certainly wouldn't, but it would certainly reduce the burden on our inspectors that go and do those jobs, and the customer inspectors as well.
What about the robots themselves? Is there any way possible to have them, I don't know, on board as part of the engine, or do you bring them in,
Well, yeah,
feed them in through the
maybe.
hole, and they work?
Yeah, currently the thoughts are putting them in when they need to be used. However, there's a kind of thought process if you, for example, operating a submarine or a civil nuclear site, both of which we manufacture power plants for, where you could say, well, weight is not necessarily such a big option. So if we carry those tools around with us, or maybe permanently embed them in the case of a kind of civil nuclear example, you could maybe use it as a maintenance vehicle without ever having to send someone in. And those are kind of quite high level drivers, but obviously reducing a person's exposure to radiation is quite a big driver too.
Yeah, no, definitely. Yeah. Or if something is in service in a very difficult environment, like you said, nuclear reactor, or I don't know, deep underwater or up in the air all the time, it'd be hard to service it. Yeah.
That's right. And we're
Are there
talking
any
also
other,
about.
Okay.
We were talking earlier about problems that we know about, and in terms of kind of reducing maintenance burden and things. And generally speaking, we try to make sure that whatever we develop in our community between ourselves and the University of Nottingham and other partners, we try to make sure that we've got a very, very kind of specific target that we're trying to address. So, and we've got kind of business cases around that, etc. But there's also room for quite speculative possibilities. So we've been working with other universities in the US actually in terms of making miniature crawling robots, and this could offer multiple benefits in terms of being able to inspect large volumes of things very quickly, but in a maybe collaborative way. So if you were to feed in maybe 10 little beetles and they've all got cameras on their backs, your computer is looking at every video screen from each one of the beetles, and they're all kind of walking to different parts of that big volume, that big, say, combustion chamber, for example, and it quickly builds up a map rather than somebody having to spend 10 hours trying to map it themselves with one big floppy piece of spaghetti.
That makes sense. Have you, maybe this is silly, but have you literally had engines in the lab and put a snake in them with a camera?
Yeah.
Or
an actual snake. Not yet. No, that would be quite an interesting prospect. Yeah.
Any last surprises about your work? Any things that you've learned that are really unusual or interesting?
I don't think it's particularly unusual necessarily, but I guess one of the things I've learned from doing this job is collaboration is really important, and you can't do anything on your own. And it's something that we really rely on our collaborative partners, both in the academic world as well as the kind of smaller, medium-term enterprises. And we work with a big range of companies, but we're also funded by either the EU or the US government or the UK government, etc. But it's kind of one of those things I'd always say, and when our seniors ask us, is why are we doing lots of these kind of long, take ages research projects? They take 5 years or whatever. In fact, I'm being a bit unfair. They are very supportive, but I'd always say you don't know what you might end up developing throughout those 3 or 5 years. We've got a very clear goal, and we're going to use our time to develop something for that goal. But along the way, there'll be some unintended developments that will spill over, and we could maybe, because we're close to our internal customer, the guys that go out and perform these repairs, they're very good at seeing those opportunities and saying, well, that thing that you've developed there, we could just use on its own in a manual way rather than on the end of a robot, for example. We can get some quick benefit we can get some quick benefit from some of those projects that on the paper look long and kind of maybe expensive, but actually when we kind of use them in the service and potentially sometimes for something that we had never considered doing, then there's always some benefit to be had.
Well, I wonder if
what you can come up we hadn't considered.
Yeah, I was wondering if you can come up with a great technology that works. Maybe it could be shrunk down tremendously and then used in the human body to fix it.
Well, yeah, I'd love that. I mean, it's we went to a medical conference last year. We were kind of invited to talk about some of the work we've been doing for our jet engine work, and there's some very interested surgeons in the room. Obviously, there's some very direct parallels. There's very different approaches that obviously the both industries take. But yeah, some very interesting possibilities. And some of the guys actually in the University of Nottingham have done a bit of work on spine surgery, actually. So this the robot that we made for reprofiling a big thread on a pressure vessel. One surgeon was kind of walking through the facility one day, and he's kind of saw some stuff we had on posters and things, and thought, well, actually, that could maybe be used for scoliosis. I was going to say repair, back repair. It's kind of spinal correction surgery. So I'm not sure where that is at the moment. It's kind of, I think they're looking for funding, or I'm not quite sure actually. But it's one of those things we're quite happy to kind of keep investigating, because like we were talking about, unintended consequences and pain. Maybe it's not just the small things that you develop along the way of designing and developing a big project. It's maybe other industries that we hadn't really considered.
I know it's gross, but you can think of parasites burrowing their way into a host or moving around in a host. Yeah. I mean, they're moving around in liquids with no clearance, and they're still surviving. Yes. So, I mean, you probably can learn a lot from watching them. Or maggots.
Definitely. Yeah, well, that's true. Yeah. They give the maggots a pickaxe and a hard hat, and off we go.
Very good. All right. I guess last question is, where can listeners find out more about the work? Maybe, I don't know if there's any examples to be seen, or case studies. But what's a good resource?
No, there's some case studies on the web. If you have a look for, if you go on, probably the best way to do this is go to Rolls-Royce.com and find on our media area. We've got a section that's around the intelligent engine, and this is to do with our kind of new service offerings and how we're trying to be more connected and have more contextually aware and kind of better sort of engine communications, I suppose. And some of those projects that I've described to you today, you can see in video form on there.
Oh, very cool. Okay.
There'll be some other links to other areas such as the University of Nottingham as well, and on YouTube, etc.
Excellent. Well, James, I really appreciate you coming on the podcast, and it's been really interesting. And oddly enough, I had a personal story that's maybe a little bit similar. So thanks for being here.
Yeah, quite. My pleasure. Thank you very much for your time.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you.